All right, so these are just a list that I happen to come up with. There isn't a finite list of different spectroscopies, but this just gives you a flavor of the kind. And there's some overlap here. So we talked about UV visible absorbance. All right. Well, that turns out to be, at least for spectrophotometry, one of the most common techniques. All right, UV visible absorbance measurements. There's also infrared. All right, infrared absorbance, which you'll also see as FTIR. We'll talk about that later. That's Fourier transform infrared. It's the same thing, just different kind of instrument, but it's measuring the infrared absorption. You have flame spectroscopy. That's the kind of thing which you may have done in your first semester general chem lab, where you just take some, say, sodium on a wire and you put it into a Bunsen burner and you can see the colors coming out, the different colors. So you put anything into a flame and it's going to emit, and again, these are going to be atomic emissions. So you're looking for various metals mostly in flame spectroscopy. You can make that more sensitive by coming up with this ion-coupled, inductively coupled plasma atomic emission. That's similar to flame spectroscopy, but much more, and we'll talk about this, it's much more stable. It has more energy, or it's more power, so that it's more sensitive. And you'll see this a lot. It gets used a lot because it's so sensitive. And then there's, it's not really quite different, but laser spectroscopy, where sometimes the light source is a laser. And that they give it a different name, although there's a lot of overlap because you can use that laser for fluorescence, for instance, or even absorption. Then the fluorescence spectroscopy, which we just talked about, where you shine light in at one wavelength and it comes out at a different wavelength. This is usually going in near the UV, and it comes out maybe in the visible. And then there's atomic absorption, right, which is similar to UV-VIS, but specifically for atomic species. There's another one called Raman spectroscopy. In this case, you use a laser. It's almost always an argon ion laser. So you send in light, and you're not looking for that argon ion laser light to come out, because most of the light that comes back out is the same as the wavelength as the light you put in. Most of it just scatters and comes right back out. But what can happen is that laser light, of course, a laser has a very specific wavelength. Unlike the white light that goes through a spectrometer. When you put white light through a spectrometer and it comes out, it's still somewhat broad because it's only as good as the spectrometer, but only as good as the monochromator that made it monochromatic. But lasers can be very monochromatic. So there's really only one wavelength that's coming out of that tool, that laser. And so then what happens is that light interacts with matter, and it shifts the energy just by an amount equal to the vibrational bands. So you can use this Raman to look at vibrational bands. And it's somewhat like infrared, but it's different. You're putting in a strong light, and you're looking for a wavelength coming out at a different wavelength. It's just shifted. And then we have nuclear magnetic resonance, which is, again, this is the nuclei, almost usually hydrogen nuclei. We're looking for, and we'll talk about this more later, it's in the radio frequency range. So these are all of these spectroscopies I've listed here are putting light in and then measuring light coming out. All right. Well, except for, I guess, flame and ICP. That's just looking for light coming out. The energy went in the terms of a plasma. There was electrons or something. Things were bumping around, and there was a voltage involved. All right. But there are other spectroscopies, all right, which don't necessarily involve light. They can, but because this, so here are some of the others. Mass spectroscopy, right? Mass spectroscopy, you take an atom or a molecule and you ionize it, and then you measure how much it weighs. What's the mass? And if it's a complicated molecule, you break the thing up and you end up with different peaks. As the thing falls apart, you get different daughter ions. You'll use this in various places, but in organic chemistry, you'll see this. So you get a spectrum, but the spectrum is in terms of mass. You get different masses. And usually, if you're lucky, the highest mass peak there, the highest mass will be the mass that you started with, right? The mass that you started with. There's another one called secondary ion mass spectrometry, or SIMS, S-I-M-S. This is in the field of surface science, where you're starting with a solid surface. Most of these other things are liquids or gases, but this one here is, I guess, all the rest of these here, or most of the rest of these, are surface techniques. Which is, what the heck do you care about surface techniques? Well, there's a big industry. Maybe you've heard of it, the electronics industry, where they do a lot of stuff, with silicon wafers and so forth, and you're working on the surfaces, and sometimes you just want to know, you don't want to know about the bulk of it, which may be a silicon wafer. You want to know what that top layer was. What is really on the top of that thing? So secondary ion mass spectrometry, what you do is you send an argon ion in, or something, or an oxygen, something like that, an argon ion in, so you know what you're sending in. That argon ion comes down to that surface, it smashes into it, and provides enough energy that something else comes out. Well, whatever's on the surface comes out. So if you have silicon on the surface, you'll see silicon coming out. If there's silicon and oxygen, or maybe there's a little bit of a dopant there, there's some selenium or sulfur, you'll see those too. So you're looking for the different atoms usually that are coming out. Although I have seen something like this done with molecules, where you have a frozen, it's more like mass spectrometry. You have a frozen organic sample or a biological sample, and you come in there and you, maybe with a laser, and you ablate some of whatever was on that frozen sample and cause it to go into the gas phase and measure its mass. So there are lots of different variations on these techniques. But secondary ion mass spectrometry is looking at the mass of what was on your surface. X-ray photoelectron spectroscopy, or XPS, that can be done with surfaces or with gases. So if you have something like say an argon ion, or an argon molecule, argon atom, right? And you hit it with an X-ray. An X-ray has enough energy to ionize it if you give it enough energy. And we're not looking at the absorption. What we're looking at is when that photon comes in, it ionizes the molecule, and it takes that electron, removes it from wherever it was in the atom, and sends it off as a free electron. It's no longer attached to that atom. All right? And when it comes out, the energy of that electron will tell you what the energy of the state where it came from is. How much energy did it take to ionize it? Because the total energy that you started with, which was the energy of the X-ray, right? You take that photon energy. That photon energy is going to be equal to the binding energy, the energy that was holding that electron into its orbital, plus the energy of the electron that's emitted. So if you know the energy spectrum of all the electrons that are emitted, you can work out what all the binding energies were. So you can see all those energy states in the argon atom, right? All the different shells. But you don't have to do this just for ions. You can do it for molecules, and you can do it for solids too. You can do this for solids and see what's happening to the atoms that are on the surface. Again, it's very surface sensitive. Auger electron spectroscopy is similar. You send in, instead of using a photon, as you did with X-rays, you actually send in an electron. So you send in a high-energy electron, smashes into the surface, and it emits a photon, if I have that right. And that photon energy is related to the energy of the states where it came from. And then there's, this one's different, or X-ray spectroscopy, or X-ray diffraction. Right, this is used for single crystals. This is how, remember you heard about these fellows, Watson and Crick determined the structure of DNA. Well, DNA was, when they were looking at it, was in a crystal. Right? So the DNA had been crystallized. It was in solution. You dried it out very carefully, and you can do this with a salt crystal or any other kind of crystal. If you have a single crystal of it, actually you can do some things that aren't single crystal, but anyway, it has to be crystallized. And then depending on the energy or the angles that the X-ray gets diffracted, so the X-ray will be diffracted by the spacings. You talk about this when you talk about solid state chemistry. You might have seen this if you took, in your first semester general chemistry class, when you talked about solids. This is how you learn about the spacings in crystals. is with X-ray diffraction. And there are other kinds of X-ray spectroscopies. Okay, all right, these are just different types of spectroscopies. Let's now focus on a few of them. All right, starting with the most common one, which is UV visible spectrophotometry. All right, this is just absorption spectrum in the UV visible range. And so this absorption, which you've learned a lot about before in other classes, follows Beer's law. Right? And Beer's law is this one here. This is Beer's law. It says that the absorbance, what's the absorbance? Well, the absorbance is you take the transmittance, right? And this is different than the transmission. The transmittance is the ratio of the light coming in, that's the P0, the light coming out over the light coming in. So this is a number between 0 and 1, right? Either you get all of the light coming back, going through, or you get half of it, right? This is some fraction from 0 to 1. That's the transmittance. People don't tend to use transmittance. They tend to talk about transmission, and then in particular they talk about percent transmission, and then you would say, well, there's 30% of the light is going through, or 60% of the light's going through. So you see transmittance or transmission spectra. But for Beer's law, you need to use the transmittance. You have to turn that percentage into a fraction or into a decimal number. So that's what this A is, right? The absorbance is the fraction of the light that's going through, or actually it's the log of that. Sorry, the transmittance is that fraction you take, which is a number now between close to 0 up to 1. You take the negative log of that, right? So if the transmittance is if you have 10% of the light going through, right? So then the transmission is 10%. The transmittant will be 0.1. Transmittance will be 0.1, right? 0.1. Then you take the log of 0.1, right? The log of 0.1 is -1. And then there's another negative in the front here. So the absorbance, all right, is going to be 1. So if the transmission is 10%, the absorbance is 1. If the so let me write that down. The transmittance and the absorbance, all right? Transmittance is like transmission, only it's a fraction. So if your transmittance is 0.1, your absorbance is 1. If the transmittance is 0.01, right, only 1% of the light's going through, then your absorbance is 2. Right? Transmittance is 0.001, it would be 3. Right? So this is a log scale. And that log scale, right, absorbance, is now proportional to the length of the light cell. How far did the light have to go through the cell? Or how much interaction was there between that light and the material? And that's usually done in centimeters. Right? Right? And then the concentration, the molarity of your sample, right, is proportional to the concentration and the length of the cell. So if it's not very absorbent, you need to have a longer cell to be able to detect it very well. Or maybe if it's too absorbent, you want a shorter cell. Or you don't have much material, you can use a shorter cell. And the concentration, of course, that's whatever you happen to have, or you can make it more dilute if it turns out that it's absorbing too much. And this other number here, which is the extinction coefficient, that's specific to the particular compound you're dealing with, and it's specific to the wavelength range you are. So this actually is a whole this is the spectrum. The extinction coefficient is when you see it a spectrum, it's really you're plotting the extinction coefficient because it's a function of wavelength. So you decide when you're doing an experiment what wavelength you're going to work on with what compound, and that will define the extinction coefficient. Or actually, they're calling it the absorption coefficient. I get those confused. The extinction coefficient is something different. The absorption coefficient. In this case, it's the molar absorption coefficient because we're dealing in molarity. All right, so it has the molar absorption coefficient has the units of per centimeter per meter. All right, so this is how you're going to do. You're going to use Beer's law when you're measuring absorbance in the UV visible range. So what are you going to put your sample in, right? If your sample's a liquid, for instance, or even a gas, what are you going to put that sample in? So there are different kinds of containers called cuvettes. All right. So the standard one, the very standard one, is a little thing it's 1 centimeter on a length. So it's 1 centimeter. The inside is 1 centimeter. And it's a square. So it's a square profile, and it's 1 centimeter. And that's, if you use a standard 1 centimeter path length, then you don't have to worry about it's the absorbance per centimeter. And so since you only have 1 centimeter, you don't have to worry about the centimeter anymore. But sometimes you don't have enough material, or it's absorbing too strongly. And so then you can get something that may look like this, which has a 1 millimeter path length. Or maybe it doesn't absorb much at all, and you want to have a real long path length, right? So here's something with a cylindrical thing with a real long path length. You fill if it's a liquid, you fill this whole thing up, or you can even flow a gas through here, or fill this with a gas. Sometimes you have only a little bit of material. So this one's got a very small profile entirely inside here. It's small, and it's called a microcell. Of course, your problem is you have to make sure that your light beam, right? Your light beam, as it comes through, has a certain size. And if your light beam is very big, you're not going to get much absorption if your cell's small. So you've got to look at the instrument design and make sure that your light is focused at a very small area to get it so it is in here. When you use one of these bigger ones, it's always, the light beam is always small enough that you don't have to worry about the other edges, or you hopefully don't have to. Here's one that has it's a flow cell, so you're flowing something through it for whatever reason. And this one's a thermal cell. Maybe your sample has to be heated or cooled for some reason. Most likely heated. Okay, so there's different shapes of cells of these cuvettes. All right. Now, what are you going to make it out of? All right. What are you going to make this cell out of? Well, if you're in the UV-VIS, you have to make it out of something that's transparent. Right? But it has to be transparent in all the wavelengths that you want to use. So, glass comes to mind, standard glass. Well, glass is transparent only over a certain range. It says here 340, which is a little bit into the ultraviolet, very little bit into the ultraviolet, which is 400 nanometers. And it goes out into the infrared. It says here 2.5 microns, 2,500 nanometers. If you want to go further into the ultraviolet, because sometimes things absorb in the UV much below, glass starts to absorb as soon as you get out of the visible, you can switch to quartz or other materials. See, this now goes down to 190 nanometers, which is maybe very important to go down lower. But it's more expensive, of course. All right, so there's trade-offs. If you want to get really cheap, and you would like to throw out your sample when you're done, these had dollar signs. Here you have penny signs or cent signs. You can make it out of polystyrene, but polystyrene, you can see, doesn't go into the infrared very far. As a matter of fact, none of these go into the infrared very far. Methacrylate, or some other cyclic olefin copolymer. So these are some sort of really cheap materials. And they tend to use a lot of these in biological systems, hospitals, medical, because they don't want to have to clean these things out. You don't want to expose people very much. So it's much better just throw things away. And a lot of that gets done in hospital kind of settings. Okay, so you have a cell of a certain length. All right, so let's just, I know you've learned this many times before, but let's just review in case you haven't got the hang of this. Beer's law, all right? Remember, Beer's law. We're going to use Beer's law to figure out the absorbance, all right, which is that absorbance is that symbol, I guess we were using E or epsilon, which is the molar absorbance coefficient. This is a sample that we know the concentration. Here's the molarity of iron 3 plus, and we're going to measure it at 530 nanometers. Okay, and the absorbance is this is the absorbance is 0.46. Remember, it had to be between 0 and 1, so it turns out to be 0.46, 46%. And we luckily used a simple path length of 1 centimeter. So that's the path length. And what we want to do is calculate the molar absorption coefficient. This is pretty easy because we already gave you the absorbance, all right, of 0.46, remember, which is the negative log of the transmission, or the transmittance. This is the negative log of transmittance. So all we do is we apply Beer's law, A equals epsilon CL, but in this case we're looking for the absorbance coefficient, all right, and so we just solve for that, and you get A over CL, and we plug in, all right, the 0.46 unitless, and then the concentration here, and the path length, and you come out with 8.5 times 10 to the 2 per molar per centimeter. Right? So Beer's law. So Beer's law gets used all the time when you're doing quantitative work, especially in the UV-VIS. It's great, right? What could be simpler? Well, a little bit simpler maybe. The words could have been a little simpler. And this, if this wasn't a logarithmic number, that would be simpler. But anyway, it happens to be the log of the transmittance. But does it always work? You know, is Beer's law work? Is it perfect? I mean, it is a law, right? Beer's law. But it turns out it doesn't always work, right? There are other complications that can occur. So let's talk about some of these deviations from Beer's law. First of all, you have to assume that the material is relatively dilute, right? On the order of 0.01 molar, right? Or less. Could be 0.0001, you know, something very low concentration. Because once you start to get above 0.01 molar, remember, you know, water, pure water is 55 molar. So, you know, something that's that is 1 molar is pretty concentrated. And what happens is when that happens, that whatever's in solution, whatever your sample is, it's not just surrounded by the solvent. The actual solute molecules are actually bumping into each other also, right? So you start to get solute-solute interactions. And that can change the absorbance coefficient, right? Because now it's not just copper 3 plus. It's not just copper 3 plus in water now. That was your sample, copper 3 plus. Copper 3 plus in a lot of water. Now you've got copper 3 pluses bumping into copper 3 pluses. And so that affects the coefficient. The other thing that happens is the index of the solution. You're assuming that your solution has the same index as water, because if things are very dilute, you can treat the index, remember this is the optical index, as that of the solvent. But that will start to change as you start to get more concentrated. So that's another concern. The other thing that can happen is that there can be some chemistry going on when you get an absorbing species at higher concentrations. It may change the structure, right? Because there could be some equilibrium going on there, and as you get to a large amount, it changes things, right? So it may not all be in the same state that you think it is. The other thing that can happen is you're measuring the absorbance at a particular wavelength, but if the instrument is not just measuring that one wavelength, because again, these spectrometers have what we call a bandwidth, they're measuring over some small range of wavelengths. If you change the range of that wavelengths, it can actually change the average absorbance in that range. So you have to worry about the instrument's bandwidth, especially if you're on the edge of an absorbance band. When there isn't much light coming through, right, because your sample is pretty opaque, right? It's too thick, it has too much absorbance or too concentrated, or the path length is too long. So you hardly get any light going through. At that point, you have to worry about the detector seeing stray light, right? If there's any light, the detector is going to find it. And so if you're trying to look down at very low concentrations, you'll have to worry about that, low amounts of light, right? And there can also be things happening if you put a cell in there, you know, because we'll talk about this when we get down to talk about calibration. But you had to somehow calibrate the instrument so that you knew when you had 100% light or when you had 0 light. Well, if the cell you put in there for the 100% isn't exactly the same as the cell you're using for the sample, maybe it's scratched up, maybe it's the light beam is hitting the edge of it or something like that, then you can start to get deviations there. And the other, on top of all this, it's just very difficult to measure very low light levels or very high light levels. So when you're getting, I'm going to go back to transmission, because I don't get confused with transmission. That if you have 100% transmission, that means you have the same amount of light going through as you had for your standard, your empty cells, say. If it was in water, it was pure water. You put a pure water in there and you measure the transmission. All right, now you put your sample in there and it's very, very dilute. It looks just like pure water. Well, if you're getting almost the same as your original 100%, it's hard to measure the difference between 100% and 99.99. It's just very difficult. And on the other end, if you're down there below 1% at 0.001%, that's difficult to measure for several reasons. One is that you might have noise, the 0 part drifts, because it depends on electronics. There's electronics that warm up in there, and things can drift. Even sometimes it drifts because somebody's talking on the telephone nearby, or there's a rapid transit vehicle that's going by, and you can pick these things up. Vibrations in the building. And on the other end, as things warm up, the amplifiers that are in there can change everything changes. So you don't want to measure things that are too high or too low, right? You'd like them to be in the middle of the range, between say 10 and 90% would be ideal. Something in the middle of the range. It's much more accurate to make a measurement in there. Okay, so that's how we're going to use Beer's law to measure the absorption of something, and this can be done sometimes very easily. If you're measuring copper 3+, it absorbs nicely in the UV visible region. But a lot of things don't absorb where you want them to absorb, because you've got this machine that measures in the UV visible, and if your sample doesn't absorb there, are you out of luck? Well, not always, all right? Because sometimes you can combine chemically your unknown sample, which has something in it, with something that you put in there. So for instance, if you have any one of these trace metals, right, aluminum, arsenic, cadmium, chromium, a whole bunch of trace metals here, there are things you can add that make it absorb light, or you combine it with something. And you can do that with some inorganic compounds, like if you're looking for chlorine, right, or fluoride, which don't necessarily absorb in the UV visible by themselves, but you put something in there that they combine with. You have to know something about the chemistry, what you're looking for, right? And it can happen with organics too. Here's some surfactants, phenol, right? So for instance, here's an example. Lead plus, just lead plus, doesn't absorb in the UV visible region. But if you put in some dithiazone, which I have no idea what that is, right? You put some of that in the solution, it combines with the lead, and now the thing makes a dithiazone lead complex, and that does absorb. All right. So you put this in, if there was no lead, it wouldn't absorb. Right. So and you can calibrate this kind of thing, and as a result measure low quantities of lead plus where you couldn't otherwise do it. And this gets used all the time. So as a result, the UV visible is one of the most frequently encountered quantitative analytical methods that's used. All right. It's and not just for looking at elements like these, right? It's used for total serum protein. These are clinical samples. These are in hospitals, for instance, serum cholesterol, uric acid, serum barbiturates, whatever those are, glucose. I know about that one, and protein-bound iron, all sorts of things, right? All right. They're also, so these are all in a biological or clinical setting. It's also used in a lot of industrial applications. It's used in pharmaceuticals, right? Drugs, in food, in the food industry, the paint industry, glass, making glass or metals, right? It's also used in, I mentioned forensic applications before. There are also other kinds, for instance, to analyze narcotics, right? You get pulled over, there's this little baggie that they found in your car, and it's got some white substance in it. That's how they're going to figure it out. They're going to stick it into one of these instruments. They're not going to make somebody back at the lab take the drug, right? No. And in fact, for drug testing, I don't know if this has ever happened to you, but you get pulled over and they make you breathe into a breathalyzer, right? You have to breathe into this breathalyzer. So you breathe into the breathalyzer, right, and it's going to measure the ethanol in your breath. And this is a spectroscopic technique. What it does is that you breathe into the machine. It takes some of that breath, puts it into an acidic solution that happens to have potassium dichromate in it, right? It produces chromium 3+, right? The ethanol reacts with the potassium dichromate, giving you chromium 3+, which then absorbs in the visible at 440 nanometers. And so I read that 25 micrograms in your breath, when you breathe out, if it's 25 micrograms, that corresponds to the legal limit, if it is, of 0.1% alcohol, right? So that's a spectrometer you're breathing into. I mean, it's only set up to measure that one wavelength, but it's a spectroscopic technique. Okay. Now, sometimes you can easily measure. You can set up your instrument. Maybe you're breathing into a breathalyzer or something else, and you don't have to worry about other things in there. You know, what else is going to be in your breath? Or you made the sample and your technique is only going to measure one species. But sometimes it's not so simple. Things get in the way. There's more than one thing in the sample, for instance. And that can make things complicated, right? Make it much more difficult if you've got a mixture of things. And I think you've run into this. In Chem 251, apparently you did an experiment, number 4, about the spectroscopic analysis of soft drink, and you had a couple of overlapping absorption bands. And so the way you deconvoluted this was to measure the absorption at those two wavelengths, and then you sent this through a 2x2, you inverted a 2x2 matrix in order to turn that to figure out how much was due to two different chemicals, right? And if you're so lucky as to have to take Chem 461, which I taught one time, right? You do this experiment called size exclusion chromatography, where you have this column and you put stuff in the column, and they're going to have you put these 3 things in the column. There's B12, blue dextrin, and hemoglobin, all right? So you've got some of that in your sample, and they're going to go through this column and come out at different times. And so you take samples at different times coming out of this column, and you put them through a spectrometer. And they tell you to measure it at 4 different wavelengths. This wavelength, this wavelength, this one, and this one. You measure at 4 different wavelengths. But what they don't tell you, people who wrote the lab manual at least, so you've got some strong, what I did here was I took the spectrum of pure hemoglobin, blue dextrin, or B12, and those are the 3 different colors here. So the red one here is the hemoglobin. And you can see the hemoglobin has strong absorptions at 2 different bands, right? But it's still absorbing at some of these other places, and because of some instrumental artifact, which I didn't have time to figure out, it went below 0 here. But it's even absorbing over at this wavelength here. So there's a lot of overlap going on. And if you're looking for the blue dextrin, well, that absorbs here at the same wavelength as this one. So how are we going to figure it out? Well, you can imagine you now have 3 different materials. You need to make them, and you've got 4 different wavelengths. So maybe you can come up with a 3x3 matrix and invert it, pick 3 of those wavelengths. And I'll leave this for you when you do this experiment in Chem 461 to invert that 3x3 matrix, which again you can do with Excel, and then try to figure out the concentrations of each of the species. Because the way it's described in the lab manual there, it isn't so simple. Okay, all right. So that's mostly absorption and the UV visible. Next, we're going to switch gears and talk about some other kinds of spectroscopies, other types of spectroscopies.